Hello, everyone. Okay, so this is differential equations, and the idea here is we're going to find approximations using three strategies. Two of them we've seen before in AB. The third one, called the Euler's method, you have not seen. It is a BC only topic. So I will do two examples. One of them we will do with an equation or a differential equation that's separable so that we can actually see the answer and see how good our approximations were. And then the other one we will do with one that's not separable, which is the whole reason why these approximations exist. Okay, I'll try to go pretty quick. So the first equation is already here. Here's your differential equation. It's a differential equation because it's dy dx, the derivative, and it's in terms of x and y. And I have given the initial condition 2, 1. Okay, the first approximation strategy that we have is called a slope field. And we saw these a lot last year. It was a big AB topic. And basically what it is, beautiful, is, it's good enough. You are going to draw little sections of what the curve would be based on the shape of the curve. So we start with, let's try 1, 1. If you plug 1, 1 into the derivative, so dy over dx at the coordinate 1, 1, you would get 1 times 1, which is 1, which means if the curve goes through 1, 1, it has a slope of 1. And how does that look? A slope of 1 is like rise 1, run 1. So we draw a little piece of the slope or the curve that has a slope of 1. That's the idea behind a slope field. And you just do that for as many points as it asks you to do it for. So if we do another one, like let's say the coordinate 2, 1, if we find the slope at 2, 1, we plug 2 in for x, 1 in for y, and we get a slope of 2, which is just steeper. So you look at your slope for 1 and say, okay, at 2, 1, we're just going to do a steeper positive slope. And we're really paying attention to the fact that it's positive and fairly steep. And then you keep doing this for different values, depending on what they want. So I picked the initial condition 2, 1, so we definitely want to test it there. So you don't have to show all the work. If we plug the coordinate 2, 1 in, oh, we just did that one. Let's plug in 0, 0, give me a slope of 0. Any of the x coordinates would give you a slope of 0, by the way. Same thing with the y's. That happens fairly often. Let's do a negative 1. So negative 1, 1 would give me a slope of negative 1, which would be in the opposite direction. If I plugged in negative 1, 0, we already have that one. That would give me a slope of 0. If I plugged in negative 1, 2, that would give me a slope of negative 1 times 4, which is negative 4, which is very steep but negative. So that's the idea. This would be a very positive slope. So you just have to go through and sketch the pieces of the curve based on the slope. And then with that, we can sketch a what's called solution curve through our initial condition. So we know the curve goes through this point, which means if it does, it has to pass through this. So here we go. Let's try to sketch the solution curve. Well, based on what's going on, it looks like it's getting steeper as we go this way. So I imagine it goes something like this here, but it looks like it levels out here and then it kind of flips. And as long as you don't go horribly against kind of the flow of your slope field, you are correct. Because this is just an approximation. Remember, these are approximation strategies. So this is called a slope field. You plug into the derivative and graph sections of the slope based on what you get from the derivative. Okay, that's the first one. The second one, we also did in AB. It's called a linear approximation. And a linear approximation is nothing more than making a tangent line at your initial condition and using it to approximate another value. So for example, I'll say use a linear approximation to approximate f of 3. So what do? Well, you make a tangent line at your initial condition, and then you plug 3 into the tangent line, and that's really it. So let's make our tangent line. Y minus our y coordinate, which the given y coordinate is 1, equals the slope. Well, how do I find the slope? I plug my coordinate into the differential equation, and I get 2 times 1 squared, which is just 2, times x minus my x coordinate, which is 2. And then I isolate y. So I have created my tangent line. So essentially what I'm doing is this. If I actually go to my slope field picture, you're making a tangent line here. And now we are going to plug in 3 to that tangent line. So f of 3 is approximately what you get when you plug 3 into the tangent line. So 3 minus 2 is 1. 1 times 2 is 2. 2 plus 1 is 3. So approximately 3. So we get our tangent line approximation. But you can see that because the concavity of the curve is positive, or it's concave up because the second derivative would be positive, we can see that's an under approximation. We'll do more of those later as we go. That's another thing we did a lot last year, where you have to find the second derivative. If it's positive, you know you have an under approximation. I'm not focusing on that quite right now. So this was called a linear approximation, when you make your tangent line and then you plug into the tangent line. We like these problems because they're not too bad. Okay, so it's the third one. That's the new one. That really is just a formula you have to memorize. And this is called Euler's method. Euler, named after the same mathematician that came up with Euler's number E, or showed how that number kind of comes to be. He developed a system that's basically this. Rather than finding one tangent line, you can find multiple tangent lines and just keep adjusting based on what's happening. So the idea is this. You're going to, instead of going all the way to the coordinate, like let's say I wanted to approximate f of 3 and do a linear approximation, we're going to use a linear approximation to approximate f of 2.5, and then we're going to use that value and make a second tangent line that gets an even better approximation. So sounds complicated. It's really not, but there are 2 formulas you have to know. And here's how I like to describe the formulas. I say to get the new x coordinate, you use the old x coordinate plus what we call h. What is h? H is the step size. We'll talk about that in a minute. That's the easier one. Here's the one that typically students always seem to forget. The new y coordinate is you use your old y coordinate plus your step size times the derivative when you plug in your new, or your old x and your old y. So it's kind of like the tangent line a little bit, because you're multiplying by the derivative times something and then you're adding the y old, just like kind of did here. But let me show you how this works. It seems more complicated than it is. So we'll start here. Same differential equation. So we will still use the differential equation, dy over dx equals, what was it again? Xy squared. And we'll still use the same initial condition, 2, 1. So I know at 2, my y coordinate's 1. So I want to approximate, again, we're going to approximate f of 3. But this time I want to use what's called 2 steps and Euler's method. So if I'm trying to get to f of 3 using 2 steps and I start at 2, the first thing is, well, how big is each step? Well, if I'm going from 2 to 3 and I want to get there in 2 equal steps, to get from 2 to 3, that means I have to go to 2.5 first, and then I have to go to 3. So your step size is this distance right here, between 2 and 2.5. In other words, what did you add to 2 to get to 2.5? 0.5. That's your h value. So our h value is going to be 1/2, or 0.5. So we'll use that when we plug into the formula. So here we go. To get the new x coordinate, you use your old x coordinate, which is, what do I mean by old? I mean your initial, 2, plus your step size, which is 0.5. And nothing too exciting here. My new x coordinate is 2.5. Amazing. How about to get the new y coordinate, though? To get the new y coordinate, you take your initial y coordinate, or your old y coordinate, which is 1, and you add 0.5 times what you get when you plug this coordinate into the derivative. So plug 2, 1, into the derivative, we get 2. And we do the work. And 2 times 0.5 is 1. 1 plus 1 is 2. And congrats, we have now found our first coordinate at 2.5, comma 2. We're halfway there. Guess what? We just do it again. Except now this becomes our old coordinate. And we use this instead of using 2, 1, and we just do the process again. So we're doing 2 steps here. We're going to do the process 2 times. So do it again. To get the new coordinate, use your x old, and now that's this guy right here, 2.5, plus our step size does not change. We're still doing a 0.5 value for our step size. And look, we have reached the coordinate we are trying to approximate. So our x new coordinate is 3. But what about the y new? Well, we use our y old, which was 2 from the previous step, plus 0.5 times what we get when we plug this coordinate into the derivative. And this is where the calculation gets a little bit worse because we're going to have decimals. So remember, you're plugging into the differential equation. So it's 2.5 times 2 squared. So a lot of times these are calculator problems. This one I think is okay. I think we can do it without a calculator. Let's see. So our new y coordinate would be 2 plus 0.5 times 2 squared is 4. Luckily, 4 times 2.5 is just 10. 2.5 times 2 squared is 10. And then 0.5 times 10, half of 10 is 5, so 2 plus 5 is 7. So Euler's method yielded a value of 3, comma 7. Did you do that correctly? Let's make sure. 2.5, 2 squared is 4, 4 times 2.5, yep. And half of 5, perfect. And that is a better, supposedly, approximation than we got in this step. So in this step we got 3, but if you noticed, look, the tangent line didn't account for the fact that this curve is getting very steep very quickly. So really, we know the true value of the curve was way higher. And even based on my solution curve, I knew that that was going on. So it looks like that's not a bad get. Like Euler's method was a better approximation for what's probably going on. And now, in this case, we can actually see how good Euler's approximation was. So the last thing, we use these approximation strategies. I actually want to find the particular solution and see how we did. So let's actually go through and find the particular solution, because why not? Because in this case, we can. So good practice for the particular solution. We're going to divide the y squared over. We're going to multiply the dx over. This is not a natural log. It's negative 1 over y equals 1/2 x squared plus c. Oops. The initial condition, if we remember, was 2, 1. So we're going to plug in 2, 1. And we get negative 1 equals plug in 2. 2 squared is 4. 4 divided by 2, 2 plus c. So it looks like c is negative 3. All right, so that means we have a particular solution when I sub in c that looks like this. 1/2 x squared minus 3. We just need to isolate y. How do you do that? Well, here's what I would do. This is a fraction on the left. First of all, you can get rid of the negative by flipping the sign on everything. And then if we want to get it out of the fraction, you flip this side, and then you flip this side. And the easiest way to do that is just literally flip it. And lo and behold, we have now found our particular solution. So how did our approximations go? Let's see. If I graph this in Desmos, I have, y equals 1 divided by negative 0.5 x squared plus 3. Nope. 3. So you notice with this initial condition, this is the graph we're dealing with, this piece right here. That gets steeper and steeper and steeper as we go. If we had negative values, we'd be down here. But for positive values, we have here. And look, we were approximating it at 3. Now, interestingly, it gives you this value down here, but it's kind of funny. This one, it's giving you a very big value based on what we think here with the initial condition 2, 1. Did this go through 2, 1? Let's see. Oops, I lost my graph. 1 second. Yeah, it did. Interesting. So this one happens to have a vertical asymptote there. Huh. So this part works out. I'm just confused on why we would be getting a negative value because I still feel like it should be positive, 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 positive. But that's interesting. Point is, the approximation works for this, and had it continued that way without being the down part on this, it would still have worked out the same way. But we're going to try it on the next one because most of the time you use these approximation strategies when you can't find the particular solution. But in this case, that's interesting that it worked out that way. Huh. This one was a little less clean because I think it's the fact that the differential equation, the way I defined it, once you have bigger values, you end up being negative. Huh. Interesting. Didn't know that would do that. Oh well, let's do another one. But our solution curve did match up with what's going on in this section. Although, yeah, with this initial condition, we would have had this piece. It's kind of funny that it ended up being this piece also. I wasn't expecting that. Oh well. All right, let's do it again. So I'm going to show you one more with a equation that's not separable, which is this one. dy over dx equals x plus y. And the initial condition, we'll make it something basic. Let's do 1, 2 this time. Flip it. All right. So slope field, you would just plug in. Linear approximation, you'd make a tangent line and plug in. Let's do Euler's method, though. So again, the formulas to remember are x new equals x old plus h for the step size, and y new equals y old plus h times the differential equation when you plug in the old coordinate. All right. So this time, let's go to approximate f of 3. And let's use Euler's method with 2 steps again. Typically, it is 2 steps. On the AP test, it's a lot of Euler's method with 2 steps. With 2 steps. Okay. So look, we're starting at 1. We're trying to get to 3, and we are taking 2 steps. So what is my step size? Well, to make it so that I get there in 2 steps, the middle step is going to have to get me to 2. So in other words, this is my step size. And to get from 1 to 2, that means the step size is a very nice 1. So I chose a problem that's pretty nice. Most of the time, you're going to be dealing with a half or a fourth or something like that. But for this case, we'll keep it a nice whole number step size. All right, so here we go. To get your new coordinate for x, you take your old x, which was 1, plus your step size, which was h. And congrats, that's the easy one. The y new is a little bit trickier. You start with your old y coordinate, which was 2, plus, and in this case, it's the step size 1 times what you get when you plug this coordinate here into the derivative differential equation. And 1 plus 2 will be 3. And lo and behold, we get our new y coordinate, which is 2 plus 3, which is 5. And that is the first coordinate in our Euler's method approximation. But we're not done. We've gotten to 2, but we're trying to get to 3, remember, so we have to do it one more time. So to get our x new, we start with our x old, which was 2 again. Or sorry, it was 2. We started with 1, but it's 2. Sometimes you will have a repeat coordinate, believe it or not. That actually happens fairly often. Plus, our step size is still h, so there we go. We made it to 3. But it's the y new that's going to look a little different. We start with this coordinate now, plus our step size, which is 1, times the differential equation when I plug in this coordinate. Remember, this becomes the old coordinate when you're trying to find the next one. So 2 plus 5 is 7, and we get an answer of 5 plus 7, which is 12. So our approximation for 3 is approximately 12. And again, this is a case where because the function, I'm guessing, this differential equation causes it to be concave up, the linear approximation is not very good because it only goes so far as to account for the fact that the function was increasing, and then you get your approximation. Euler's method kind of does this. It approximates halfway. So if you started here, halfway, and then once it finds this value, you stop here, and then you readjust, and you look at the slope here. And you say, oh, look how steep the slope is. Well, instead, let's make a second tangent line that has the same slope as the curve here, and let's get an even better approximation. Now, Euler's method you could do with as small a steps as you want, as many times as you want. So it's actually a pretty cool strategy if you had a computer program that could do this, where you could do 1,000 steps all of like 0.001 and plug it into a computer, and then it would give you a really good approximation, which is the type of stuff you do in differential equations, which is a calculus course in college. You deal a lot with these types of differential equations, which are non-separable, so you can't find the particular solution. Remember, there's no way to get x and y on one, or x on one side and y on the other. So Euler's method was the thing that pops up every year on the BC exam. It is a cool approximation strategy for approximating differential equations. And that's about it. So your homework is a lot of Euler's method, linear approximations, and slope fields. This one kind of confused me a little bit. I don't know why the approximation was down here, but I'll have to think about that. Anyway, that's that. All right, goodbye.